Okay, if there are no questions, okay, so today is the last formal class of this session. And as you must have realized, we have never come close to half the course, or maybe a bit more than half the course. Uh, I have uploaded a video which starts talking about Lie groups, just at a very preliminary level. Just we have just talked about U1 and SO3 so far, and at least the SO3 part you have already seen before. In one of our first classes, this is just a sort of recap which puts everything in one place. The next video will be uploaded tomorrow morning. That will be more about SU3, SO3, SU2, SUN, and so on. And the final one, which will talk a bit more about formal properties of Lie algebras, on Monday. So that and today's class, that's basically it for the syllabus for this NSEM. So the 3 videos that we will have on say continuous algebras, continuous groups, Lie groups basically, and today's class, that forms that, plus of course whatever was done with finite groups before, all of these would be in the syllabus for the NSEM. And then there will be other videos, as I promised, later on, which talks about these things in more detail, but they will come slowly and they will not be in the exam. So is that clear to everybody? Is there any confusion about that? Since nobody is saying anything, I'm assuming it's clear to everybody, or I hope I'm still connected. Let's just check. It seems I'm connected, so everybody did hear that. Okay, any questions, queries, comments? You know, many of these memes have been going around that students just switch on their login and then go to sleep, but they at least designate one person to keep on responding to the teacher. Is that what's happening now? It seems even that one person has gone to sleep. Okay, okay. At least one person has not gone to sleep, or more than one person, I guess. Anyway, so today's class essentially will be quick introduction on one of the very important Lie groups, which actually has immense consequences in physics. This is the Poincare group. We have already studied this in a way beforehand. Remember when we talked about semi-direct products, we talked about how the Poincare group is a semi-direct product of the Lorentz group and the translation group. Both of these groups are infinite groups, and both of them can be parameterized rather neatly by continuous parameters, and they actually are Lie groups. Poincare group is also a Lie group. So what we are going to talk about is the Poincare group algebra, how to derive it, and on top of that, how to actually get. So what kind of consequences that algebra has is a very deep question, very important question. I'm not sure whether I will be able to cover that in today's class. That's a rather important topic. So, and I don't really want to burden you with that in your exam because that is a bit involved. So what we will do is we will try at least to derive up the Poincare group Lie algebra and try to talk about some of its consequences, but not so much. But before that, what we need is a sort of quick introduction as to how Lie groups come into quantum mechanics. And this is a big subject, so I'm not going to talk about all of it here at all. What I'm going to do is I'm I'm actually talking about Lie algebras in the videos that I've uploaded. I've just talked about two very simple ones in the first place. And we have not formally talked about what a Lie algebra is. But if you have listened to those videos or watched those videos, you would know that we are talking about there specifically about matrix groups. Okay. And the reason why we are doing that is the following. Matrix groups are actually a lot easier to handle because much of the complications that arise can be sort of handled within the simple rules of matrix multiplication. So because of that, if you confine yourself to matrix groups only, which form a large bulk of important groups in physics, important Lie groups which occur in physics, we can do without many of the technical difficulties which arise when you talk about a general Lie group. However, it is actually important and also quite interesting to see how you would tackle Lie groups in general without restricting yourself just to groups of matrices. And I'm going to just give you a glimpse of that right now, although I'm not going to go through the whole calculation. Once again, for this part, the best quick reference would be Weinberg. UFT, volume 1. This would be chapter 2, I guess. Yeah, chapter 2. Chapter 1 in Weinberg basically is the history of quantum field theory. Chapter 2 is where the technical stuff starts. And it essentially starts with a study about, okay, so although many of you may not be interested in quantum field theory in the long run, but what it does is, what Weinberg starts here starts basically with quantum mechanics, how symmetries get introduced there, and talks specifically about the symmetry that we are talking about here, Poincare symmetry. And the field theory part, of course, starts a lot later. Chapter 2 is basically quantum mechanics and symmetries. And this book has a reputation of being very difficult, but that's essentially because it actually is is very, very detailed and very first principles. In most quantum field theory books, you would find many results which are taken for granted or to be introduced later and so on. Weinberg doesn't take that route. Weinberg essentially tries to prove everything from scratch. Doesn't really succeed in doing everything from scratch, but goes a long, long way. And that is why it has this reputation of being very difficult to understand if you were talking about the whole book. On the other hand, things like these are very difficult to come by in other books, but Weinberg has a wonderful exposition on that. So if you can't follow what I am saying, I will try to paraphrase Weinberg a bit. I will try to explain a bit more about what he is saying. But basically, if you can't understand me, I'm pretty sure if you try reading that, it would be easy enough for you to understand. At least once you have got an introduction to it. So general situation in QM would be something like this. Suppose we have a group of transformations which we are calling a group of continuous transformations which have been parameterized by some bunch of parameters. So so this is not quantum mechanics yet. I'm just talking of transformations which you can carry out. Some kind of transformations could be rotation of coordinates, could be a Lorentz transformation, could be a Poincare transformation, could be some internal transformation which you do in internal coordinates, whatever, doesn't matter. These transformations depend on some parameters, right? And essentially the idea behind a Lie group is that the transformation depend smoothly on the parameters, especially in this sense that if you were to compose two such group elements, T theta is a group element for a particular value of theta. Okay, theta here is not really one theta, it's basically theta 1, theta 2, theta 3 up to theta d, if there are d parameters involved. So theta here is a shorthand for a tuple of d quantities. So this is one group element for a particular value of theta. Theta bar is another value of theta, that is theta 1 bar, theta 2 bar, and so on. So that's another group element. If you multiply the two together, you are going to get a group element, right? So it also has to be T for some parameter, which of course will depend on the parameter here will depend on theta and theta bar. So it's some function of theta bar and theta. And the specific nature of the Lie group essentially is encoded in these functions. These functions essentially contain most of the information you want to know about the Lie group. Okay, there are some, at least as far as Lie algebra part is concerned, which is what most physicists are concerned about, this function would be enough to tell you what the Lie algebra is. In fact, you don't even need to know the entire function for that. We are going to come to that soon. But basically, the idea is that this function should be an analytic function of theta and theta bar. So that is basically what we mean by a Lie group. A Lie group is one in which this composition rule is an analytic function of the arguments. That is, of course, the resulting parameters depend on the parameters which define the group element that went in, and you get this. Okay. Now, one important point, theta equal to 0, by convention, we choose this to be the parameter for the identity element. That is T for 0 will be the identity of the group. Okay. So that's really just a choice of your parameters. When you choose your parameters, you do it in this way, that when you put all the parameters equal to 0, you get the identity. But that actually puts a huge restriction on this function, because it tells you this is what? If you look at this, this is the parameter for T of theta, T of 0. T of theta, T of 0 has to be T of theta, right? So if the parameterization is done properly, this must imply that f of theta comma 0, in fact, f is, although I'm writing this as f, this is really d different functions, f1, f2, f3, and so on. So for each of these functions, fa theta comma 0 has to be theta a. And that's not only the case, fa 0 comma theta also has to be theta a, right? Okay, so if you put one of the arguments equal to 0, of course, when I say one of the arguments equal to 0, I mean all its d components equal to 0, then the function will have to return the other argument, the non-zero one. So is this clear to everybody? The question, of course, is meant to mean, if you don't understand this, please speak up. Okay, that might seem like another trivial thing to say, but notice that if this is true, if you couple this with the fact that this is a differentiable function, a smooth analytic function means you can write a power series for this, right? So power series will have terms which are independent of theta. Then there will be terms which are linear in theta. So theta, there are several thetas. So theta a, ta. For later convenience, I will put in the I. Plus I theta bar a ta. So this is the linear part. And then there will be quadratic parts. What would quadratic parts be like? Half theta a theta b.
Sir.
Yeah. Go ahead.
Sir, from that T of f theta comma 0 equal to T of theta, how exactly do we say f of theta comma 0 equal to theta?
Okay, so T of theta times T of 0, this is the identity, remember?
Yeah.
So this is equal to T theta, right?
Huh.
So that means f of theta comma 0, since your parameterization is unique, right? So when you parameterize only one bunch of parameters, that's when it's a good parameter. I say it has to be a good parameterization. You don't want multiple parameter values to give you the same result. Okay. So f of theta 0 gives you the t, which is the same as the t which you get from theta. So f of theta comma 0 has to be theta. Okay. Clear?
What if, I mean, it's not possible that it can be some theta plus k, or
So then if that would be different parameters giving you the same group element. That would simply mean your group parameterization is bad. Now that can happen, by the way. For example, theta plus 2 pi can give you theta, right? Is that
oh,
okay? For rotations, of course, not always, but for rotations about an axis. But those would be distinct, discrete pieces. And if you now if you impose continuity, you can easily show that you start with theta, you should get to theta, not somewhere else. If the function also has to be continuous, theta plus 2 pi will be a sudden jump all of a sudden, right? Suppose you make 0 very tiny, you stay close to theta, then you suddenly change to theta plus 2 pi. That would go against the smoothness of the function. The typical idea is locally, at least, this parameterization should be good. That is, nearby values of theta should give you nearby t transformations. And not only that, here, at least within a local range, the nearby parameterizations cannot be many to one. You can have many to oneness in the parameterization, but only if those parameters are well separated from each other. That happens all the time. Okay, but locally, at least, if you look at a small region of the, so basically what you're saying is the parameters at least has to be good in a small local region. And that is what we actually use when we talk about manifolds. We don't talk about the whole thing, but we talk of small patches. Just like a small piece of any curved surface looks like a flat region, that is the kind of thing that we are using here. Okay. So what we are demanding is our functions should function. Of course, the function should have to give me the same theta values, which will give you the same t. Right? That much is of course correct. Right? This has to happen no matter what. The point is you can always choose your parameterization function such that when it gives you the same theta, same t, the corresponding thetas are also the same. But the moment you choose this, this is what your demand is. Is that okay?
yes.
But now I have written several things. For example, then you could have mixed quadratic pieces like theta bar b, theta bar theta c. So two thetas, two theta bars, theta bar and theta, TBC, let's say, and so on, and higher order terms. But now this is the general statement, right? Any smooth function of theta and theta bar can be expanded like this, plus higher order terms. These are, of course, derivatives. Now, given the fact that when you put in this, you have to get theta, what does that tell you about C0? So if you put in both as 0, what will you get? FA00 has to be what? Because these zeros mean 0 vectors, 0, all d of them are 0 here, all d of them are 0 here. What's the result? The result is the eighth parameter, which is of course a single number. How much is that?
0.
So what does it tell you about C0? You put in both zeros here, you have to get a 0. So what does it tell you what C0 is?
It should be 0.
Yeah, because all the other terms will go away when you put them both 0, right? Good. So there's no C0. Fine. Now, suppose I put in theta bar equal to 0, which is what this says. I put in theta bar equal to 0 and just put a non-zero theta. I should get theta A, right? Only theta A. Sorry, what am I saying? I'm making stupid. Okay. There's no I here. I just jumped across to 7, and maybe I will just change the notation here, not call them TATB, because I'm going to use TATB later for other purposes. Theta A, alpha A, theta A. And I'm not going to call this TBC either. In fact, well, I should really talk about a single function, not about the entire bunch of functions. So Please excuse me for messing this up, but what I really should say here is the eighth F should really be. Okay, let me just write this again. I am sorry, I just badly messed this up. Because I forgot that I was writing for the eighth component of a bunch of functions. Eighth function here. So what I should have really said is CA0, which anyway I've seen is 0. And I don't really need an I for this. So let's put in a theta A. Sorry, not theta A. Alpha AB theta B plus beta AB theta bar B. So this is what really I should really be saying. Half. Now this should be lambda A B C theta B theta C. This is the general form. Is everybody clear about this? Because I'm talking of the eighth function. Now, please don't confuse FABC with the F here. This, of course, is a single number. So what I wrote earlier was nonsense. This is the correct expansion. Okay. This is for the eighth function, so there's an A superfix on each one of these terms. And now, can anybody tell me what should alpha AB be? Just try putting theta bar equal to 0. What happens? This term goes away. This term goes away, right? This term goes away. But what you should get is theta A.
Should be delta AB.
Yeah. Theta A should, this should give you theta A. And this immediately tells me that this should be delta AB. Very similarly, this should also be delta AB. The delta symbol. And so, this part becomes very simple. This part simply becomes theta A plus theta bar A. But can anybody tell me what happens to this? What should this be? The quadratic part. Should it be there? If I put in theta bar equal to 0, this term goes away, this term goes away, right? I should get back exactly theta A, not an approximation, exactly theta A. So what does it tell you about these terms? Yes? So just put in 0 here. You should get exactly theta A and put in theta bar equal to 0 on the other side. What do you get about this term? Yes?
B plus C should be equal to A.
B plus C should be equal to A.
To match the
Those
question.
are not, by the way, don't confuse these with powers. These are stuff, theta 1, theta 2, theta 3 are different parameters. This is not theta. This is not theta to the power beta B plus C. This is not theta raised to the power B. Each of the, if I want to raise it something to a power, I will write this with a bracket and write the power separately. These are indices. Just written upstairs, just because we want to use a summation convention. I've used indices upstairs and downstairs. That is other advantages of keeping track of terms, but these are not powers. This is not theta to the bar A. This is just a thing, theta 1 plus theta 2 plus theta 3 plus theta bar 1 plus theta bar 2 plus theta bar 3 and so on. This is theta 1. Sorry. If it's F1, then this is theta 1 plus theta bar 1. Not theta to the power 1. If this is the F2, this will be theta 2 plus theta bar 2. These two terms. Not theta to the power 2. This is a quadratic piece, product of two different thetas, not powers. Okay. So what can you say about this? Yes? That's not the simple. Come on. I'm just
It
asking.
equals 0.
This has to vanish. No other option. Otherwise, you will not get this result. Okay. Now you somebody might say fine, but that doesn't mean that lambda ABC has to be 0. If lambda ABC is purely antisymmetric in B and C, since you're multiplying it by a theta B, theta C, which is a symmetric product in B and C, you are going to get 0 anyway. But I don't really care. It's the total sum which is really important, and that's 0 anyway. I'm not really interested in whether what lambda ABC are. All I'm saying is lambda ABC could be non-zero and still give you a 0 value. Could be perfectly antisymmetric in B and C. It would give you a 0 value for the sum. But the sum is what occurs in our function's definition. So that's 0. Now what about this thing? So I could argue that a pure quadratic in thetas, just thetas cannot be there. Can you have a pure quadratic in theta bars? Theta bar, remember, is the first argument here. Theta is the second argument. We just saw that you can't have a pure quadratic only in the second argument. Can you have pure quadratic in the first argument?
It should also be 0.
Why? What do I do to check that? What tells me that? Okay, all you do is look at f a theta bar, comma 0. That has to be theta bar A, right? Same argument. So this will also have to vanish. What about this one? Notice that this survives both that terms. If you put in theta, look, if you put in theta equal to 0, this term goes away. If you put in theta bar equal to 0, this term goes away. So its presence will not mess up our basic demand that 0 stands for the identity, hence this function has to obey this. So up to quadratic power. So what I'm trying to tell you is this very simple statement that the function is smooth and that 0 stands for identity. That is enough to make quite a powerful amount of quite a powerful restriction about this function fa. If you were to expand it in powers of thetas, then the linear term has to be theta a plus theta bar A, nothing else possible. And the quadratic piece has to be of this kind, FABC, theta bar B, theta C, plus higher order terms. Again, you can only have higher order terms in which pure cubic in theta or pure cubic in theta bar cannot be there. Simply because when you put in theta bar equal to 0, the pure cubic in theta will survive and mess up the demand that it has to give you theta A and nothing more. Only terms you can have are mixed terms. Theta bars will also be there, thetas will also be there, and so on. For us, for the present purpose, we are really interested only in this much because that's all we are going to need. The important thing is, you have to realize one very important thing that is happening here. No matter what your group is, no matter what Lie group you're talking about, what kind of continuous parameterization you have, no matter what function you are dealing with, this form has to be there always. As long as theta equal to 0 stands for the identity, this is the form which you must have. Of course, if you change your parameterization, what might very well happen is FABC, these numbers might change. Okay. But even for the same group, just change your parameters, these numbers might very well change. But as long as you're sticking to this parameterization where identity stands for, is given by zeros, this form is automatic. So what went into this? Basically nothing but the definition of the identity and the fact that the function fa is a smooth function which can be expanded in a power series. Okay? Right? Is this clear so far? Now, when we talk about matrix groups, usually the product is automatically given by matrix products. So we will not have much occasion to look at the specific nature of this function. So if we confine ourselves to matrix groups in the rest of the lectures, you may not be able to see this kind of argument there. But that's simply because we are taking a approach which is based only on matrix groups, and we are exploiting the matrix product there. The important point is not all Lie groups are matrix groups, but this kind of argument would work for all Lie groups. So I wanted also to give you a flavor of the kind of arguments you can use in general. Now, let us come back to quantum mechanics specifically. This is for a transformation which you carry out. The basic idea of using this in quantum mechanics is something like this. You have a group of operations which you carry out, either coordinate transformations, rotations, reflections, whatever. Reflections would be continuous, but rotations, Lorentz transformations, and so on. And you have this composition rule for that. But corresponding to whatever you do to your coordinate system or to your internal coordinates or whatever operation you do on your system, the quantum states describing the system will transform according to some operator, some which we already have shown before, can always be chosen to be unitary or anti-unitary. For the time being, we are going to assume that we are going to choose them to be unitary. So for every t of theta, which acts on some space, some operation that you're carrying out, which depends on these parameters theta, there will correspond some operator in your which acts on your Hilbert space, which also depends. Actually, this is u of t of theta, but for sake of notation, we can simply drop the t. We can just go directly from the parameters themselves. So u depends on the parameters, and the basic idea is u of theta bar, u theta, has to essentially give you the same kind of idea, f of theta bar theta. This is nothing but saying that this map which maps t theta to u theta, is a homomorphism. And in physical terms, all you're saying is, suppose I do one transformation and then I do another transformation. When I do the first transformation, my quantum state changes. When I do the second transformation, it changes again. So that's what happens. Then if that is the way you do it, then this operator u theta bar u theta will act on your quantum state. If, on the other hand, instead of doing this in two steps, you directly carried out this one single transformation, which is the same as doing the two steps one after the other, this will have a corresponding u, and that will act on my state. The basic idea is, no matter how you do it, you end up with the same result at the end. Whether you do it in two steps, theta first, theta bar then, and then end up applying u theta first, then u theta bar, or you do it in one single step, you get the same result. This is something we have seen over and over again. This is how group representations work in physics everywhere. Now, what the important point here is this, that thetas are parameters which talk about transformation elements, right? And specifically, if theta is 0, then you have the identity. So we must have this one relation. U of 0 must be the identity. Okay, it's difficult to write a curly I or something, so I'm just going to write 1. But this 1, remember, is the identity on the Hilbert space. Remember, if your parameters are 0, it means that you're doing nothing to your physical system. So the corresponding operator has to be the identity. The all important thing is, suppose I carry out a very small change. Now, because theta is this parameterization smooth, I can talk about what happens when theta is very, very small. Not 0, but tiny. Let's say theta. And typically when we do that, we usually don't write theta any longer. We replace theta by something like an epsilon, just to signify that this is small. So what should U epsilon be? And this is something which you have seen several times. In fact, even if you haven't learned any group theory, you have seen this before. Last year, when you talked about quantum mechanics and connection with rotations, we did exactly the same thing. What we are saying is, if I carry out a transformation which is infinitesimally close to the identity transformation, the resulting operator which acts on my Hilbert space should be infinitesimally close to the identity. So it should be identity plus. Now, of course, when I say epsilon, I mean there are several epsilons, right? Epsilon 1, epsilon 2, epsilon 3, and so on. So this will be an operator, of course, because this is an operator, this identity is an operator, what you add to it is an operator. But this operator can be written down in this form, epsilon 1, the first small change into T1 plus epsilon 2 into T2, and so on. Basically, this is really saying that U epsilon can also be Taylor expanded in the powers of epsilon. And being physicists, and this is where I have to warn you, physicists use this, mathematicians often don't. Physicists love Hermitian operators. Mathematicians have no really special place in the heart for Hermitian operators. So mathematicians prefer not having an I and cluttering their equations up. But we physicists love our Hermitian operators, so we will put in the I. Now, let me also tell you that in the recordings that I'm putting in, I have not put in an I often. I've also said what happens when you put in an I. That's simply because most mathematics textbooks won't put in an I because no real point in putting in an I as far as they are concerned. And moreover, many things become easier to understand without the I. The I is a price we have to pay for our love of the Hermitian operators. But this is just a linear piece. Of course, there will be a quadratic piece as well. So we get something like, okay, even so even if epsilon is not if epsilon is really infinitesimal, I can just stop here. But if epsilon is small, I have to go one step further and talk about, say, and then further terms. Okay. In fact, I don't even have to use this. Okay, let me just change that a bit. I don't even need to assume that theta is infinitesimal at this stage. All I have to do is say that, okay, as long as for any theta, you can write down this as an expansion. Of course, whether you can stop in the first term at all, stop here or stop here, that depends on how small your theta is. If theta is really very, very tiny, you can drop the higher order terms. Otherwise, this is the general form that U of theta is going to take. Okay. Is everybody with me so far? Any confusions? So now we start with this basic statement, U of theta bar, U of theta, as we just claimed, has to be U of f of theta bar theta. Right? But we know what f of theta bar theta looks like. At least what fa of theta bar theta looks like. At least up to quadratic power in theta. So we are going to use that. What we are going to do is write U theta bar that's U of theta times U of theta, sorry, U of theta bar, then you have to write U of theta theta, which is 1 plus I now. At this stage, you might object that I should not really be using the same dummy index twice. But there's no problem really. All you have to do is when I multiply these two terms together, I have to remember to change the dummy index. Right? Otherwise, it's fine. As long as they're not being multiplied together, there's no problem that way. Then comes U of f of theta bar theta. But that's fa theta bar theta. I know what FA theta bar theta is. It's theta bar A plus theta A plus half okay, by the way, I don't really need the half. So if I want to, as far as I remember, Weinberg doesn't use the half. There's no reason to use a half here anyway. So maybe I'll just drop the half out. There is half in this expression. This half is actually useful for several reasons, as you will soon see. And moreover, this is really a square. That is theta 1 is also theta 1 square is also there and so on. Here there is no square term because you have theta bar B and theta C. Anyway, this thing is basically f bar A, f of A, and that has to be multiplied by TA. Then you have to multiply the, then comes the troublesome term. You have to take this into this. So this whole expression for B, whole expression for C, and so on, and multiply them together. But it's really rather easy. Why? Because we are working only to quadratic power. That means when I put in f of fb of theta bar theta, all I do is put in theta bar B plus theta B. And here I just put in theta bar C. So because we are working only to quadratic power, the actual calculation is pretty simple. You don't really have to, this looks very messy because it looks like you have to bring in lots and lots of terms, but you don't really have to do that. Is there any confusion as to why I can stop here and don't need to put in the, of course, here there should be F, B, C, D, theta bar C, theta D term. There should be half, it should be F, C, PQ, theta bar P, theta Q term, and so on. But is everybody sure why we can ignore those terms? I hope everybody is still awake.
You're just not considering the higher order terms, right? That's it, right?
Yeah, but the point really is this is already quadratic because this is linear, this is linear. You're multiplying them together. You already have second order terms, right? If you put in a second order term here, that will have to be multiplied by a theta here, right? Either a theta or a theta bar. That will be third order. That is why we are dropping it. It's not completely arbitrary. We have to ensure that we only keep terms up to second order, and all terms which can contribute to second order have to be kept. That you can't do anything about. So this is what you have to have. This has to be equal to this, right? Now, it seems like a rather trivial thing to say that these two things have to be equal, but that actually puts a huge restriction on these quantities. Now, let me point out why that is so surprising. After all I'm doing here is I'm expanding mu of theta in a Taylor series, right? The zeroth order term is just 1 because I know that when theta is 0, u theta is identity. 1 here, of course, means the identity. The first order term is some operator. I'm just calling those coefficients, which are essentially derivatives of u theta with respect to theta a. So basically del u theta with respect to del theta a. That is actually ITA. That's essentially the coefficient theta a, right? This term is actually del 2u del theta B del theta C. That's TBC. Right? By the way, I have already assumed one thing, which TBC is equal to TCB. There are two reasons why they have to be equal. One is even if TBC and TCB were not equal, that is, if T were not symmetric, then it would have a symmetric part and an antisymmetric part. And the antisymmetric part would not have contributed anything to this sum because theta B, theta C is symmetric in B and C. And because of that, I could start by assuming TBC is symmetric anyway, because the antisymmetric part would not contribute anything. And if you just go by the Taylor series version, TBC is nothing but this second derivative, mixed partial derivative. So TBC has to be equal to TCB. Okay. But the important thing is TA is the first order term, right? TBC is a second order derivative. Now in a Taylor series, usually the first derivative has nothing to say about what the second derivative is going to be like. If you knew the value of the first derivative, this is the first derivative at theta equal to 0. This is the first derivative, second derivative at theta equal to 0. If you know the derivatives at theta equal to 0, you have no idea what the higher derivatives are going to be like, right? So usually you would not expect TBC to be anywhere related to TA. But the Lie group property, that is basically the fact that U is homomorphic to T of theta, and T of theta is a Lie group with this composition rule, that plays a huge role here. And to see that, all you have to do is start with this equation and compare linear terms, quadratic terms, etc. on both sides. So what's the linear term on the left? On this side, that is, okay, let me just do one thing. Let me change the color of this. So this is the left-hand side. This is the right-hand side, of course, the one in blue. So on the left-hand side, what is the linear term? Tell me, anybody recite out the linear term to me.
ITA times theta A plus theta
So I
A
theta
bar.
bar ATA, that's I theta ATA, right? This term into identity, this term into identity. That's it. That's linear. What about the quadratic? What's the quadratic term on the left? Quadratic means 2 thetas or 2 theta bars, or 1 theta, 1 theta bar. Yes?
Minus theta A, TA.
So you're starting with this one. Okay, minus. Okay, maybe I'll write that last. But what about this? Let's start with this. There's going to be half theta bar B,
Half.
theta bar C,
TBC.
TBC, plus half.
Same term again. Not
Not
same
the
term.
same term, theta B, theta C.
Theta B, theta C.
They are different parameters, so could be very different.
Yes. Yes.
Anyway, similar terms. And then you have a minus. Right?
Theta bar ATA, theta ATA.
Okay, better to change
some
the, because theta bar
indices.
B, theta C,
Change the indices.
TBTC. I have to change the indices anyway, right? These are dummy indices. I can't use the same for both. So I've just changed both of them, one to B, one to C. So that's the quadratic term, right? Purely quadratic. What about the other side? Linear term is I theta bar. I can immediately read off the linear term. Theta bar A, TA, that's I theta A, TA. That is, up to linear terms, both sides agree. Right? So nothing comes out of, nothing special comes out of the linear terms. No condition or anything. But what about the quadratic term? Quadratic term on this side, of course, is I F A B C TA. Remember, this is a TA, but it's quadratic in theta. So there's one term. Then you have cross terms here. Now I'm sure I will not be able to fit everything here, but let's try. Theta bar B, theta bar C plus theta B, theta C plus theta bar B, theta C plus theta B, theta bar C. So all this into TBC. Now the important thing that you should, of course, note is that the quadratic pieces on both sides are not automatically equal to each other. This piece cancels out with this piece here. That's okay. I should write this a bit better. I think you should be able to read this, I hope. This TBC. So theta B, theta C into half TBC, that cancels out. Theta bar B, theta bar C into half TC, that cancels out. Right? But what you have in addition to that, half of that into TBC, right? This term, plus IFABC sorry, I somehow put this downstairs, which I shouldn't have. I really shouldn't really bother too much about the color. Anyway, theta bar B, theta C, theta. That's the quadratic piece on the right hand side. On the left hand side, what you have is minus theta bar B TB times TC. Okay. Okay. Now, one important point. I can switch B and C in the second term here. These two terms, theta bar B, theta C, and theta B, theta C bar, are they the same? Is this one equal to this? Say, of course, you can choose B equal to 1, say C equal to 2. If you choose B and C equal, then of course, no problem. They're equal. But if you choose B equal to 1, C equal to 2, you get theta bar 1, theta 2. The other one is theta 1, theta bar 2. Are these the same?
No.
Of course not, because theta and theta bars are independent parameters, right? So, but my claim is that when you contract them with TBC, then of course there's no B or C index left. But these terms, theta bar B, theta C, TBC, and theta B, theta C bar, TBC are exactly equal. Can anybody see that?
That's because TBC is symmetric, right? Or
That's because TBC is symmetric, and you can, of course, B and C are dummy indices. So you can write this as theta C, theta bar B, TCB. That we have two things. B and C, TBC is symmetric, and also another thing which we have assumed tacitly so far, and which is fine, which is if I were to switch B and C here, I will get TCB, theta C, theta bar B. Is that the same as this?
you're assuming theta and theta bar commute. So
yeah, so what we are assuming two things. We already know TBC is symmetric, so TBC and TCB are equal. But on top of that, we are actually assuming thetas are ordinary numbers. That is, they commute. The reason why I'm stressing this is, well, not something we can cover in this course. Anyway, the course is over. But if you talk of things like supersymmetry, there you would have to deal with parameters which are not necessarily numbers, but anti-commuting objects, so-called Grassmann numbers. There, on the other hand, there what you would typically have is TBC would be anti-symmetric in B and C. So again, the same thing would work. But you'd be careful. This argument works because of two things. TBC equals TCB and thetas commute. So thetas being ordinary numbers commute. So anyway, this goes away. All this. And then you can immediately read off coefficients. Since theta bar B, theta C are completely independent, you can immediately read off this result. The TBC has to be equal to minus TBTC minus IFABC TA. 。 Okay, so notice that if you know the group multiplication rule, okay, so I know basically what this function f of theta bar theta is. So I know these coefficients f of f abc. Clear? So the f abc are nothing but second order expansions of that. So if I know that and then know the first order generators ta, tb, cc and so on, the second order term tbc automatically follows. And you can push this further. You can go ahead and keep on pushing this further and further, show that higher order terms will also follow. Okay. Now some of you might say that what's the big deal about this? We have already shown this before, haven't we? We have shown that basically if you have a large transformation, you can always write that as something like this. Then end up with e to the power I theta t, which is what we have done with rotations, by the way. We have done all that, but my claim is there's something special going on here. That here meaning here, some special result was being used here, which is not true in general. So the fact that even in general, this result as a second order term can be found from the previous two is actually very, very important. Can anybody tell me what that thing is that I'm referring to here? What is special about under what circumstance does this result follow? That this follows always, but under what circumstance can you say that a big transformation with an angle with a parameter theta is basically n copies of transformations with parameters theta by n? Or can I always write this? That if I know the infinitesimal version is identity plus I theta t, I can write the finite version as e to the power I theta t. Is that always true? We have done that so far in rotations and all that. But is it true to say that this is what always follows? Yes. So a transformation with the parameter theta is n copies of transformation with theta by n. Is that always true? Please don't confuse the theta with an angle of rotation. This theta is just any parameter for any Lie group. This is always true. If you do theta by n times, you get theta. Okay, for rotations, it does happen, right? If you rotate through theta by n times, you do get a rotation through theta. Provided, of course, you're doing this about the same axis. But does it always happen? If I do a Lorentz boost with the velocity v by n times, do I get a Lorentz boost with velocity v? Then I will call you back in an hour or so. Okay. Okay. Yes. Is it true to say, yeah, you were saying, somebody was saying something, I couldn't hear that.
Is the homomorphism a condition required for it?
No, I'm not talking about homomorphism would be from one group to another. Here I'm not talking about anything like that. I'm saying if I rotate through about an axis through theta by n times, Do I get a rotation through theta? Is that yes, true or false?
For rotation, it is valid.
If I rotate about a given axis through
But the
suppose I
axis has
rotate.
to be changed for after every infinitesimal transformation. Otherwise,
Sorry, I couldn't get you. Could you just be a bit louder?
it,
I said it has to be what?
the after each rotation, I mean, you should change the
Axis.
no, not the axis, but I mean, you should transform the coordinate according to each infinitesimal rotation.
Of course, that's exactly what happens, right? But I'm not talking of any coordinate transformation or anything. I'm just talking about the actual change that happens. If I rotate through 10 degrees 5 times, do I get 50-degree rotation? Yes or no? About the z-axis, let's say.
If axis is fixed, then it's
Yeah, so for rotations, this works only if you are rotating about a fixed axis.
yes.
And that's how we derive all those e to the power minus I theta j by h cross, etc. Jn theta n hat dot j by h cross, all these transformation rules for rotation operators in quantum mechanics. But the important thing is that doesn't always work. That depends on a specific kind of parametrization. That is, basically the parametrization has to be additive. Theta 1 followed by theta 2 should give you theta 1 plus theta 2. That happens only if f of theta bar theta, if a of theta bar theta is theta bar a plus theta a, and that's it. No higher order terms. If this happens, that of course means the same for this, which means the transform operations commute. Then and only then, and not only do operations commute, the operations commute and you end up with a additive parametrization. If that happens, then the exponential works. Otherwise, the exponential does not work in general. There is a theorem in Lie groups which we will not cover now, but I will prove in one of those additional videos I'm going to make. But you can always, in a given Lie group, you can always find subgroups where the parameters are additive, and so the exponential will work out for those cases. But this is a general situation. That is, notice that even when the parameterization is not additive, there's telling you the second order term can be found out just from the first order terms. But what is actually even more important or more interesting for us is this. If this is TBC, what is TCB? It has to be minus TCTB. Right? And then these two are equal, right? TBC and TCB have to be equal, symmetric in the two indices. So what does it tell you? If you subtract the red equation from the blue equation, what you get is this equation. Right? This simply follows from the fact that TBC and TCB are equal. Just check whether I got the sign correct. I may have messed up the sign while changing over sides, but I hope I haven't. I don't think I have. So this is the famous demand that we make for any Lie group, that if you take these quantities T, small t's, which are generators of the Lie group, the transformations that occur when you're moving infinitesimally away from the identity, the commutator is dictated just by the multiplication rule for the group. And you can always find that the important thing is, take any two such generators, find the commutator, the result has to be a combination of the generators. That is, under this bracket operation, the space of all generators is closed. and CABC, the so-called structure constants. And for obvious reasons, they're antisymmetric in B and C. So that happens in all Lie algebras. Lie algebras meaning you start with a Lie group, look at what happens close to the identity, and any representation of the Lie group will mean that something is acting on states. That something also has to give you an operator which is the identity operator plus a small correction, and this small correction idea gives us the generators. Just like for angular momentum, they give us for rotations they give us angular momentum. And notice that in general, the way the group original transformations compose, that tell us what FABCs these parameters are, and that dictates what the commutator is going to be. So not only for rotations, which we had already argued in the last year, that the angular momentum commutation relation is not something specific to quantum mechanics in that sense. The angular momentum commutation relations follow trivially from the geometry of rotations, the way rotations compose, which is why all kinds of angular momentum, anything which generates rotations, could be orbital angular momentum, could be spin angular momentum, etc. All of them must have the same commutation relation. So this hugely surprising thing that or huge amount of surprise we sort of associate with spin, and we keep on saying there is something which is like a spinning particle but not really a spinning particle, etc. That really is completely, well, not worth discussing. The point is, spin talks about a system on which you're carrying out a rotation. And the fact that rotations don't commute immediately tell you how the generators will fail to commute. Not only that, it will tell you what the commutation relations are going to be. And there's no mystery about spin that way. What we have just established is that this works not only for spin and angular momentum or for rotations. This essentially works for all Lie groups. Okay. Now, I'm pretty sure most of you are tired by now, so I'm not going to really finish off what I started out with saying about the Poincare group. I will not show you the details of the calculation, but what I will do is something like this. I will quickly remind you of the relation that we had. I hope everybody remembers this. This is how Poincare group elements compose. Of course, this is x prime mu equal to lambda mu nu x nu plus a mu. Now, what we will do is we will simply say this. Suppose I have a Poincare transformation which is very close to the identity transformation. So what does that tell you about lambda mu nu? For the identity transformation, what do you have? What is lambda mu nu? If I don't have a boost at all, I'm talking the same observer. What is lambda mu nu then? Yes?
Identity plus.
Yeah. No, for no transformation, you have delta mu nu. For infinitesimal transformation, you'll have delta mu nu plus something. Let's call that omega mu nu. Okay? Now, as we had already seen before, the lambdas are not independent. They obey this relation, right? Is that okay? Everybody knows this, I hope. I think we also talked about this when we talked about the Lorentz group first time. But this is the basic defining property of a Lorentz transformation. That is, it keeps this quantity invariant, where eta mu nu is, of course, that plus 1 minus 1 minus 1 minus 1 diagonal tensor. This is familiar to everybody, I hope. Now, using this and this form for an infinitesimal transformation, you can immediately show this result, that omega mu news have to obey this relationship. By the way, omega, this is and these are different. Omega mu nu is eta mu rho, omega rho nu. Lowered. I'm sure all of you know how to raise and lower indices, right? You must have done this in relativity somewhere, right? Yes or no? You've done this before?
Yes, sir.
Yes, sir.
Raising indices, lowering indices, and so on. The point is, lambda mu nu's differ from the identity matrix elements, that is delta mu nu, by tiny amounts for infinitesimal transformations. When you take this expression, plug it in this, and just keep track of first order terms in omega. Omega are tiny, right? So higher order terms you can ignore. You will immediately end up with this relation, that omega mu news with both lower indices is antisymmetric. Okay. So that's the condition. What that means is, okay, how many omega mu news do you have overall? How many values can mu and nu take?
4.
Four each, right? So how many omega mu news can you have? How many parameters? These omega mu news are infinitesimal parameters which talk about an infinitesimal Lorentz transformation. But how many of them are there?
16.
Should have been 16, but because of the antisymmetric condition, the number of independent omega mu news.
It will be 10.
10. Why? Omega mu news alone, by the way, for the Lorentz group. How many? (16) is correct. If there were no relationships like this, it would have been 16. But this relationship reduces the number, right? What would the diagonal values be? Omega 0, 0, omega 1, 1, etc.
0.
0. So they are out of the count anyway. So 4 of them drop off. So 16 minus 4, that's 12. But out of the 12, you know 6 of them, you know the other 6 because of this relation. The number of independent parameters is 6. So a Lie group, the Lorentz group, is actually a 6-dimensional group. And that's easy to understand. There are 3 rotations, 3 independent rotations, and 3 independent boosts. They make up the entire Lorentz group. So 6. The 10 is for the Poincare group, because in addition to these 6 parameters, omega mu nu, although they look like 16, there are only 6 independent. What else are there in the Poincare group? The translations. And how many translations do you have? How many independent translations do you have? These. How many of them?
Four.
4. So 6 and 4. The 10 parameters are parameter. The Poincare Lie group is a 10-dimensional group. It's a 10-parameter group, and its group manifold is 10-dimensional. The Lorentz group itself is a subgroup which has only 6 dimensions. A translation has 4 dimensions. You can have time translations or spatial translations. Okay. Okay, so I'm not going to do the full calculation for you here, but I'm going to just give you an indication of how the calculation goes. What I'm claiming is, note that this is the composition rule for Poincare transformations, right? And that is all that you really need to find out important results like commutation relations for the generators of translation, generators of Lorentz transformations, and so on. What do I mean by generators? I simply mean this. If I do a Lorentz transform, or if I do a Poincare transformation, that is, if I go from one observer to another, if I have a quantum system, the new observer will describe the same state using a different ket. And that means that what you can do is apply an operator U, which depends on lambda and A. And this lambda and A could be finite lambda, finite A, not necessarily infinitesimal. And this U lambda A will act on the state, and that will tell you what happens to the state when you change your transformation, change your operator. But if you do two such transformations, one after the other, you should expect this to happen. That is, once again, if you do it in two steps or in one, you get the same result. That is the demand. Now, what we really do is something like this. The trick here is consider this quantity. Okay, before I go, that's something you can easily find out, right? U of what is the Lorentz transformation, what is the translation? That's easy to find out from the general composition rule that you have up here. But then what we do is we say that if my lambda is very close to the identity, that is this identity plus omega, where omega is infinitesimal, and A is infinitesimal some epsilon. Of course, that's shorthand for epsilon 1, 0, epsilon 1, epsilon 2, epsilon 3. If I take this, then the operator has to be identity, right? Plus what? Plus first order term, which will depend on these omegas and these epsilons. Now, not only on one of the omegas, but all 6 of the omegas. So what you write is omega rho sigma, j rho sigma. That is omega 1, 2, j, omega 0, 1, j 1 plus omega 0, 2, j 2. And because rho and sigma are going to run over 0, 1, 2, 3, you will get terms like omega 0, 1, j 1. You also get terms like omega 1, 0, j 0. And since omega 1 and omega 10 are negatives of each other, only the difference j 1 minus j 0, that is only the antisymmetric part would contribute. And so what we are going to do is we are going to assume j 1, j rho sigma is antisymmetric anyway. Any symmetric part would not contribute. So we are going to make the assumption j rho sigma is minus j sigma rho from the very beginning. And the half is simply put in because omega 1, j 1 plus omega 10, j 10 would give you the same term twice. The half is simply to ensure that they are only counted once. It's just convenience. And then the standard phases ploy, you put in an I. And then for the epsilon, you also have a. So these are the generators of Lorentz transformations. These are generators of translations. And the reason why I'm writing capital J for one and capital P for the other is because we identify them using the connection with classical mechanics, with essentially with angular momentum, at least as long as omegas are spatial, that is just rotations, and energy momentum. P0 stands for the energy, of course, and P1, P2, P3 for the momentum. Translation generators, time translation and space translation generators. I'm pretty sure you've covered all that earlier in a quantum mechanics class as well, this identity. But the important thing is, if I push this in here and carry out the calculation, that actually tells you what happens Okay, I'm not carrying out this calculation at all for you, but it's pretty straightforward. All you do is take this infinitesimal version, that is instead of lambda bar and a bar, put in I plus omega epsilon, push this whole thing in here, right? But on the other hand, on this side, when you take specialized lambda bar to identity plus omega and a to epsilon and keep only first order terms, this also gives you a bunch of parameters. So write down both sides, compare terms, you will end up with these expressions, whatever they are. And then the next step would be So what I'm doing here is I'm not going to ask you this in the exam, but I can very well ask simpler things in the exam to do, because this is lengthy. But what you're supposed to do is take this expression for you for infinitesimal parameters only, plug it in the middle here. You can easily show that this result is also for infinitesimal parameters on this side. Notice that if that's easy to understand, right? If I did not do any transformation at all, this would be the identity. And these two would cancel, you would get an identity. You put in a infinitesimal transformation in between, the resulting transformation can only be infinitesimal. And since both sides have infinitesimal transformations, you can use this formula on both sides and then compare coefficients of omega rho sigma and epsilon rho on both sides. And this will give you a relationship for this. For example, this will give you lambda mu rho, lambda nu sigma, J rho sigma, minus A sigma P rho. It's a lengthy calculation, not lengthy, it's slightly long calculation, but you can do it. It's pretty straightforward. And you get a similar relation for P rho. Here you get lambda mu rho, P rho. Sorry, P mu. Rho P mu. Okay. I'm just stating the results here. How you get that is you take the infinitesimal version of the transformation, put it in this expression, and then compare two sides. But can anybody tell me how to go from here to the commutator? Okay, I may have lost everybody by now, but still. Is anybody still awake? Nobody is awake, it seems. Fine.
Sir, the commutator of what?
Of J's with J's, J's with P's, all the. So notice that there are 6 J's, 6 independent J's, right? Because of this J rho sigma equal to minus J sigma rho, you again get 6 independent J's and 4 independent P's. So 10 generators corresponding to the 10 parameters that we have in the Poincare group. And I need commutators between all of them. J's with J's, J's with P's, P's with P's, and so on. That's how you get the Lie algebra. The next step would, of course, be to learn how to use that Lie algebra to make physical statements. But what about how to find out the Lie algebra? How to find out the commutators? Starting from this, how do you find out the commutators? The answer is pretty straightforward. You put in for lambda n A. That is for lambda. First, look, you started with this relationship. This is a general relationship. There's a composition rule. Then you could use that to find out this general relationship for any finite lambda, finite A, finite lambda bar, finite A bar. Then you specialize to put lambda bar and A bar equal to infinitesimal variations. And that, once you do that, that will give you these relations. But now that you have this, you can put in lambda A as infinitesimal quantities as well. What that means, and let me just show you why that will give you a commutator. If lambda is an infinitesimal quantity, let's say identity plus omega. That's the U lambda A, at least up to linear order. There are higher order terms. Then you have J rho sigma. That's here. On this side, what you have? Sorry, where did I go? Yeah. And then you need the U inverse. But what is U inverse? pretty easy to see that U inverse has to be U dagger, which is I by 2. Right, that's what the left-hand side is. What is the right-hand side? Right-hand side is delta mu rho plus omega mu rho, delta nu sigma plus omega nu sigma, minus epsilon sigma p rho. Now all you do is, if you multiply this up to the first order, for the 0th order you get identity times J rho sigma times identity. That's just J rho sigma, and using delta mu rho, delta nu sigma, J rho sigma, you again get J mu nu on that side as well. Sorry, this is okay. This is wrong, by the way. People should have. It just shows that people have gone to sleep. Of course, doesn't make sense. It has to be J mu nu minus A nu P mu. And that's what I need here as well. So just compare two sides now. Compare the coefficients of omega mu nu on both sides. Where does the commutator come from? That's straightforward. If you look at the left-hand side here, I lost the whole thing. Yeah. When you take this times this times this, that's what you're multiplying, right? Notice the first order term will be identity J rho sigma identity. On this side also, if you take delta mu rho, delta nu sigma, J mu nu, you get J rho sigma. So that cancels. Then you get the first order term, which is omega mu nu, J mu nu, J rho sigma into identity. The other term that you get is identity into J rho sigma into minus I by 2 J mu nu. So what you will get from here is I by 2 omega mu nu will be multiplied on the left by this commutator J mu nu, J rho sigma. Okay. Similarly, using this, and identity this, and this will give you a commutator between J mu nu and P mu. Just compare both sides, you will be able to write down what this commutator is going to be. So this is a very important thing that you would need to do anyway in physics. So I may not give you this highly complicated calculation to finish in the exam, but I might very well give you a simpler version which uses the same kind of argument. But the basic idea is you start with a general composition rule, then use the infinitesimal versions, and from that you try to find out the commutation relations. Okay. So let me stop here because people have already given up, it seems, anyway. And I'm going to put in further details in the videos later on. But if anybody has any questions, go ahead and ask. Yes? If you don't have any questions, let's stop here. Okay. And best of luck for the examination.